Hello everybody, and welcome to exercise 1, which gets started on page 15 of the workbook. Okay, and this is an exercise in talking about level surfaces, the concept that we introduced in example 2 on this same page. Let's read this problem together here. So a long thin rope containing insect repellent is placed along the z-axis. The density of insects at a point xyz is given by the formula p of xyz equals 5 times x squared plus y squared. Insects per cubic foot. Okay, and x, y, and z are distances measured in feet. So let's draw a picture of this. Okay, so we're in three-dimensional space, and there's the z-axis. Okay, so x, y, and z. And they're telling us that we've got this thin rope along the z-axis, so if we highlight it, it would be right here. That's the thing that's got the insect repellent on it. Okay, and part A asks us the following question. What is the insect density at the point 1, 1, 2 in three-dimensional space? Okay, well, we can calculate that by just using the formula that we're given here, so let's start by doing that. Okay, notice that the formula is missing a z, so really all that's relevant are the x and the y value. So we'll substitute those in. And let's see, 5 times 1 squared plus 1 squared is 5 times 2, which is 10. What would the units on that answer be? Okay, well, we can see that here, insects per cubic foot. Okay, so that's the density at the point 1, 1, 2. So we've answered the first part of the question. Whoops, let's try to write that a little bit more neatly here. 1, 1, 2. Okay. Now there's a second part to this question. Does the density of the insects increase or decrease as we move away from the z-axis? Okay, let's think about that for a minute. So if we go over to our picture, okay, and imagine that we're right on the z-axis somewhere, and we go away from it, notice that going away from the z-axis is going to make x or y get bigger. And so the question we're trying to ask is, what's going to happen to this function as x and y get bigger? Well, we can see that it's going to get bigger. We're going to get more values. Okay, so, or we're going to get larger values. So let's put that into words. Since our function increases as x and y increase, that should mean that the insect density is going to increase as well. Now, does that make sense practically? Okay, just kind of logically. If you think about it, it does make some sense, because if we've got insect repellent along the z-axis here, seems like the insect density ought to increase as we get farther away from the z-axis. Okay, so there's part A of our problem, and let's move on to part B. I'm going to try to keep our work in part A in the picture here if I can. Describe the set of all points at which the insect density is 20 insects per cubic foot. Okay, how would we do that? Well, starting out algebraically, it's like asking us to take our density function and just set it equal to 20. That's our starting point. Okay, let's see where that leads us. So we have a formula for p of x, y, z that looks like, let's see, sneak a peek, 5 times x squared plus y squared. Okay, let's scroll up now so that we've got all of our space. And we can work with this equation a little bit. Okay, divide both sides by 5, and we're going to get x squared plus y squared equals 20 over 5, which is 4. What is that the graph of in three-dimensional space? Well, that's actually a cylinder of radius 2. Okay, it's one of the surfaces that we looked at the very beginning of this section, centered along the z-axis. Okay, so what is this really telling us? Okay, well, remember the significance of the 20 that we have here. Okay, that was a number that we set equal to the function p. So 20 is an insect density, so insects per cubic foot. So this cylinder that we came up with, you can think of it as the set of points in three-dimensional space where the insect density is going to be 20 insects per cubic foot. Okay, so let's see if we can put that into words. So the insect density is 20 insects per cubic foot everywhere on this cylinder. Okay, and that cylinder is an example of a level surface. This is exactly the definition. We took our function, we set it equal to a constant value, and we got a three-dimensional surface. Okay. And so C asks a similar type of a question. Could we describe the level surfaces of our function in general? What shape are they? Okay, well, to get kind of an arbitrary level surface, we'd take our function, and instead of taking a specific value, okay, we'll kind of take a general constant c, set it equal to that, and just see where that leads us. So we're going to take the formula for p that we have and set it equal to c. Go through the same calculation that we did above. We're going to divide both sides by 5. Okay, and then we can ask, what type of a shape are we looking at? Well, this is still a cylinder that we're looking at. If you're wondering what the radius is, you might notice that we could get sneaky here and write this c over 5 as the square root of c over 5 squared. Okay, so the radius is actually square root of c over 5. Okay, so just to actually answer the question that they asked us, we could say something like this. The level surfaces cylinders are cylinders centered along the z-axis. Okay, and we have finished the problem.